Determinant is a square arrangement of numbers called elements representing a specific value. Representing a specific value. This shows that a determinant just square arrangement of elements. And we know that for any square arrangement, we need square number of elements. That is 1 element, 4 elements, 9 elements, 16 elements, 25 elements. That is n square elements. That is n square, need n square. So when it is 1, we represented this. When 2 elements, say 1, 5, minus 3, 6, is square element, number of row and number of columns are equal. Say 9 elements, 1, 2, 5, minus 3, 6, 8, 7, 2, minus 3. Like this. And we write these arrangements within two parallel lines, bounded by two parallel lines, not modulus. For one square element, you may mix up this with modulus, but this is not modulus. From the question, you have to understand whether it represents modulus or determinant. So in this case, there are one square, that is one element. In this arrangement, there are two square, that is 2 elements, 4 elements. It is 3 square, that is 9 elements. Since it is one square, it is called first degree, by 1 degree, by first order determinant. This is called second order determinant. Sometimes we call it degree also. Second order, and this is third order. Similarly, likewise, there can have fourth order, fifth order, nth order determinants. But our syllabus restricts us up to third order, maximum limit to fourth order. And in case of when fourth order determinants arise, we apply determinant properties of determinant to reduce that to third order. After that, we calculate everything. So these are determinants. So this is first order determinant, second order determinant, third order determinant, and fourth order determinants. So in a determinant, say we considered a third order determinant. Let this be our determinant in consideration. Now see, in this case, it has 3 square elements. And these are called rows. Row 1, this is called row 2 or second row. This is called row 3 or third row, and denoted by R1, R2, and R3. These are called column 1 or C1. Likewise, it is C2, it is C3. So in case of fourth order determinant, there will be C4 and R4 also. Now, if you observe that this element lies in first row and first column. This lies in first row, first column. This element lies in first row, second column. This is first row, third column. Second row, first column. Second row, second column. Second row, third column. Similarly, this is third row, first column. Third row, second column. Third row, third column. That's why we denote this element in general by A11. We denote this element by A11. Since it is first row and second column, so it is denoted by A12. So in Aij, I is equal to serial number of row or row number, and J represents serial number of column or column number. So in this way, a third order determinant in general represented by, in general, a third order determinant is represented by this way: A11, A12, A13, A21, A22, A23, A31, A32, A33. This is general expression of a third degree or third order determinant. So these are different values. They may be all equal, may not be all equal, may be all zero, may not be all, may not be zero. So they here AIJs are normally real numbers. Sometimes they may be variables also. So this is third order. If I want to write a second order determinant, so second order determinant will looks like this. It is second order determinant. It will contain only the element A11, A12, A21, A22. That is second order. If we want to write a first order determinant, then it will be only this. This is first order, second order, and third order determinants. See, likewise, fourth order, fifth order, and nth order determinants are denotable. And nth order determinant we represent in general, that is called general representation of a determinant, is denoted by A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN. This is called general representation of determinant of order n. Of order n. So this, sometimes we represent it in general Aij, in simple. Aij n. That represents Aij, I and j varies from 1 to n. So in short, we can represent this by this also, this symbol also, to save our time and ink. And determinant represents a specific value. So what is the value represented by this? To calculate the value of the value that represented by this determinant, we have to expand this determinant. Before we expand a determinant, we have few other things to learn. Let us consider this determinant, and name of the determinants are represented by capital letters. Let A be a determinant. We consider a third order determinant, and same concept, same definitions for higher order or lower order determinants. We always will discuss everything we considering a third order determinant. Now see, we know that this is R1, this is R2, this is R3, this is column 1, this is column 2, column 3, or simply C1, C2, C3. Now see, in these elements, they have a common representation, AII. AII. Now see, 1, 1, 2, 2, 3, 3. So all the representing letters are equal. Digits are equal. They are called diagonal elements. They are called diagonal elements. These are not diagonal elements because this is 1, 3, 3, 1 of this form. They don't have these two I and j equal. So when I and j are AI in Aij, I and j are equal in the elements with I equal to j are called diagonal elements, and this is called diagonal of the determinant. So a determinant has single diagonal. Single diagonal. So diagonal element you understood? That is very important sometimes. Next, see, few special. If all elements are 0, then the determinant will look like 0, 0, 0, 0, 0, 0, and 0, 0, 0. 0 determinant. 10. So this is a special type of determinant whose all elements are 0, but this determinant has no special need or special role in case of determinant. But this kind of matrices, in a matrix, when all elements are equal, that is a very important matrix. In that case, we call that a 0 matrix, but we can't call it a 0 determinant because determinant represents a specific value. There are plenty of determinants whose all elements are non-zero, but value is 0. All elements are non-zero, but value is 0. But if we see that only the diagonal elements are non-zero and other elements except the diagonal elements are 0, then this is called diagonal determinant. This is called diagonal determinant. Same definition in case of matrix, we call it diagonal matrix. So after going through determinant, matrix become very easy. Few properties are differ. They will differ by few properties, operations are differ, but more or less all concepts are so. So it is a diagonal determinant. Diagonal determinant. What is definition of diagonal determinant? Definition says if Aij is equal to 0, when I not equal to j, and not equal to 0 when I equal to j, then it is called diagonal determinant. So in a diagonal determinant, all diagonal elements are non-zero, but the non-diagonal elements are 0. So this is not a diagonal determinant. No more a diagonal determinant because one diagonal element is also 0. Its one diagonal element is also 0. So to be a diagonal determinant, to be called a diagonal determinant, all the diagonal elements must be non-zero. Must be non-zero. They may be positive, they may be negative, but they are non-zero. But other elements, except the diagonal elements, must be 0. This is called diagonal determinant. Here is a special type of determinant. See, this is a diagonal determinant. 5, 0, 0, 0, 5, 0, 0, 0, 5. This is also diagonal determinant. This is a diagonal determinant, but in this, what is difference between these two? In this case, all the diagonal elements are equal. In this case, all the diagonals are non-zero, but maybe unequal. So when all the diagonal determinant elements are non-zero and equal, in a diagonal determinants, when the diagonal elements are equal, then it is called a scalar determinant. Scalar determinant. So what is scalar determinant? Scalar determinant is a diagonal determinant whose diagonal elements are equal. This definition we never use in determinant. Has no use in determinant. It has no use in determinant. So it is very less used in determinant. We can say that it is not used in determinant. It is useless definition, but I defined it. Why? Because there is the same definition in case of matrix. There is a diagonal scalar matrix. In case of matrix, scalar matrix is a definition is there. To keep the parity between these two, I repeat this. Clear? So this is called scalar determinant, but I am again telling that this has no use in, no specific use, no useful use in determinant. Now this is a diagonal determinant and scalar determinant, but its all diagonal elements are 1. This is called denoted by I3. Since its order is 3, it is denoted by I3 and it is called identity by unit determinant. Third order unit determinant. Third order unit determinant. Clear? It is called third order unit determinant. So what we learned? Up to this, we learned what are the diagonal elements called, why they are diagonal, called diagonal element, how many diagonals are there. Then diagonal determinant. What is diagonal determinant? Diagonal determinant is a determinant whose diagonal elements are non-zero. All diagonal elements are non-zero. And all non-diagonal elements are zero. A special type of diagonal determinants whose all diagonal elements are equal is called scalar determinant. Very few use. And when the scalar, the value of the diagonal elements is 1, all the values are 1, then it is called identity determinant or unit determinant of that order. And since it is of third order, it is denoted by I3. For second order, it is called I2. For 10th order, it is called I10. Now see, in this determinant, there are some specialities. What are these? A12, that is this element, first row, second column. And the element is second row, first column. So A12 and A21 are same. Both are 3. Similarly, A13, first row, third column, first row, third column. And 31, third row, first column. Both are 7. Similarly, in case of diagonal elements, they are obviously equal. So no question of checking for diagonal elements. So I am checking for non-diagonal elements. A23, that is second row, third column. That is equal to 2 and 32 is also 2. This is the property we observe. Aij is equal to Aji. If any determinant possesses this property, then it is called symmetric. Symmetric determinant. This is called symmetric determinant. Clear? Very easy. Symmetric determinant. Next come this determinant. In this determinant, in comparison to this, now see A12 and A21, 1, 2 and 2, 1, their sum is 0. That is A12 is minus of A21. Likewise, A13 and 31, their sum is 0. Say A13 is minus A31. A23, 2, 3 and 3, 2, if we add these two, it will be 0, is minus A32. And you observe that all the diagonal elements are 0. Because in this case, Aij is equal to minus Aji. And since in case of diagonal elements I and j are equal, so Aii is equal to minus Aii. If I replace j by I for diagonal elements, I and j are equal. So that implies 2Aii equal to 0. That implies Aii equal to 0. That's why all the diagonal elements are 0. Note that all the diagonal elements are 0. This is almost like, looks like symmetric determinant, but it is not equal, just negation. This is called skew symmetric determinant. Now, what is definition of skew symmetric determinant? A determinant is called skew symmetric if Aij is equal to minus Aji. And it is a very common question, so that in a skew symmetric determinant, the diagonal elements are 0. And proof is here. You have to write it since the determinant is diagonal skew symmetric, so Aij is equal to minus Aji. For diagonal elements, I is equal to j implies Aii is equal to minus Aii or Aii equal to 0. Hence, the diagonal elements are 0. Very simple proof. So this is very common question, 2 marks question. Prove that the diagonal elements of a skew symmetric determinant are always. Skew symmetric determinant has 2 other very important and interesting properties. What are that? Value of skew symmetric determinant of odd order, first order, third order, fifth order, seventh order, 19th order, 99th order, all are equal to 0. Value of this determinant is 0. And first order, for first order, it is 0. First order skew symmetric determinant. It is symmetric also. Value of skew symmetric determinant of odd order is always 0. That we will prove later. Not now. We will prove after learning some properties of determinant. We will prove it. That is a very simple question. So, and if it is of even order, and value of skew symmetric determinant of even order is always a perfect square. For example, if we consider a determinant of second order, 3 minus 3, 0. And you already know to expand this, its value is 9. So general form is second order skew symmetric is 0a minus a0. Now see its value is a square. So see, likewise, we can prove that the fourth order skew symmetric determinant is also a perfect square. Eighth order, 20th order, general proof is if order of a determinant is 2n, the order of a skew symmetric determinant is 2n, then it is perfect square. It has a mathematical proof, but which is that is out of our syllabus. So we won't prove this. We'll just use the concept. Now see, the question arises whether there is any determinant which is both symmetric and skew symmetric. Example I already given to you. This is symmetric and skew symmetric by definition. For second order, it should be like this. For third order, it should be this. Because these two, for symmetricity, you have to make these two equal, and for skew symmetricity, you have to make these two of opposite side. So this is only possible when both are 0. So the 0 determinant is symmetric and skew symmetric both. 0 determinants are symmetric and skew symmetric. Next, look at this determinant. Look at this. Now, in these two determinants, observe that a diagonal divides the determinant into two parts. In this also, the diagonal divides the determinant into two parts. This is called upper triangle, and this is called lower triangle. This is called upper triangle, this is called lower triangle. Here also there is lower triangle and upper triangle. Now see, upper triangle in elements, including the diagonal elements, are non-zero, and lower triangle elements are 0. Clear? Upper triangle elements are non-zero and diagonal elements, and lower triangle elements are 0. This is called upper triangle determinant. Upper triangle determinant, but it has no specific uses, just a definition. Let A be a determinant. Now, we interchange the rows into columns and columns into rows. That is, first row was 257. We make 257 as first column. The first row is converted to first column. Second row, 369, becomes second column. Third row, 28 minus 3 becomes third column. Now you observe that we change rows into columns. Now see, the column become rows. First column becomes first row. So this method, we call this method changing rows into columns and columns into rows. Clear? If I give you any determinant, can you do this process? Very easy. This is called A transpose. This is called transpose of A, and denoted by A transpose. So taking transpose of a determinant is very, very laborious and very, very tough process. You have to change columns into rows and rows into columns. So it is very tough job. You may need a high duty crane. Note that if it is a symmetric determinant, then after taking transpose, it remains unchanged. For symmetric determinant, after taking transpose, it remains unchanged. Now take the transpose of this, A transpose. First row 257 becomes first column. Second row 569 becomes 569. 793 minus. See, they are same. They are same. So in case of symmetric determinant, A transpose and A are equal. Again note that all the diagonal determinants are symmetric. All the diagonal determinants are symmetric. So taking transpose of a diagonal determinant makes no change. But If it is skew symmetric determinant, then what will happen?
নেগেটিভ হয়ে যাবে তো স্যার।
Skew symmetric determinant. Skew symmetric determinant. It becomes skew symmetric determinant. So elements become 0. Now C is skew symmetric determinant. If we take the transpose, the diagonal elements remains the same. So minus 5 becomes, this minus 5 become plus 5, minus 7 become plus 7, plus 7 become minus 7, and a minus 9. See first 0 minus 5 7, 0 minus 5 7, 5 0 9, 5 0 9, minus 7 minus 7 9, minus 7 minus 7 9. Now see, they have changed. These two determinants changed, but still it is skew symmetric. But still it is skew symmetric. But in case of symmetric determinant, A and A transpose are equal. Equal in all sense, equal in all arrangements. Clear? So what is transpose? That is very easy. So you can take transpose of any determinant. So you will try it. May take any determinant of any order, at least for up to 4th order, and take their transpose. Our next discussion is about minor and cofactor. What is minor and what is cofactor? And minor and cofactors are concerned with elements. These value of minor and cofactors are concerned with elements. Their elements corresponding. For example, if A11, A12, A13, A21, A22, A23, A31, A32, A33 be a third order determinant, then minor corresponding to A11 is denoted by M11. M11. The minus corresponding to A12 is denoted by M12. Likewise, minor corresponding to Aij is denoted by Mij. Clear? This is not definition. This is just notation. What is minor? So Mij, definition of Mij. Mij is the determinant obtained by eliminating ith Mij. This element Aij, this is corresponding to Aij. Aij lies in ith row. So I eliminate ith row, and element Aij lies in jth column and jth column. So ith row and jth column we have to eliminate. So after eliminating, for example, so M11, what will be M11? To get M11, we have to eliminate the M11 means first row and first column. That's we eliminated. So what we get? A22, A23, A32, A33. This is M11. Let this be a determinant A. So what is M11? 11 means this element is A11. So we have to eliminate this and this. So we have to eliminate this row and this column. So after eliminating, we get 0, 5, minus 3, 16. So what is M12? 12 means first row, second column. So we have to eliminate first row and second column. After eliminating first row and second column, the only remaining elements are 8, 5, 2, and 16. Second, say A, M, 2, 3. So it is second row and third column. Second row is this and third column is this. So after eliminating, we get 3 minus 2, 2 minus 3. Look at the only visible elements. 3 minus 2, 2 minus 3. So this is 3 minus 2, 2 minus 3. Likewise, you can write all the minors. That is M11, M12, M13. That is first row and third column. First row, third column. After few sums, you don't need to cover the row and columns. You will easily find the values. First row, second columns are covered. So 8, 0 and 2 minus 3. 8, 0, 2 minus 3. M 2, 1, 2, 1, that is first row, second row, first column. Second row, first column, so only remaining is minus 2, 6 and minus 2, 16. Likewise, we can find all the minors corresponding to all the elements. Now note that the determinant was third order and minors are second order. Likewise, if the determinant has order 4, the minor should be of third order.
3.
Minor third. If determinant has order n, the minors has order n minus 1. If determinant has order 2, the minors are first order. Likewise, if it is determinant of order 1, then it has no minor. It is adult. It is no more a minor. After minor, we come to cofactor. Like minor, cofactor is also defined corresponding to elements. Cofactors are also corresponds to elements. Cofactor of A11, C11. Likewise, cofactor of Aij element denoted by Cij, and cofactor is defined by Cij equal to minus 1 to the power I plus j into Mij. So Mij we just learned. Only we have to multiply Mij, the minor, with minus 1 to the power I plus j. Then we will get Cij. That's why sometimes Cij is defined as minor with proper sign. Minor with proper sign. Sometimes we define cofactor as minor with proper sign, and rule of determining sign is by multiplying Mij with minus 1 to the power I plus j. For example, if the determinant is 3, 4, 5, 2 minus 6, 8, 11 minus 3 and say 9, then C11. Since it is 1, 1, it is minus 1 to the power 1 plus 1 into M11. So this is, it is M11. So for C11 element, so for A11 element, the cofactor and minors are same. But for C12, it is minus 1 to the power 1 plus 2 M12. So it is minus M12. But for the C12 element, cofactor is negation of the minor. C13 is equal to minus 1 to the power 1 plus 3 M13. Since it is 4, so it is equal to M13. So notice that when the sum of the digits is even, then C1, Cij and Mij are equal. When it is odd, so Cij and Mij are of different sign. If Mij is 10, Cij is minus 10. Likewise, we can define C21. It is minus 1 to the power 2 plus 1. M21, so you minus M21, and so on. So this is definition of cofactor. Now, showing this by observing this method, when this sum of these two is even, then cofactor and minors have no difference, and when it is odd, my cofactor is just negation of mine. Now comes value of a determinant is obtained by taking sum of the products of elements of any row or column with corresponding cofactors. Now I will explain it by an example. Let this be a determinant. So as per the definition of value of a determinant, we can find value of the determinant by multiplying, since we have given permission to consider any row, so we can consider as first row, we can consider as first column, consider first column, second column, third column, anything. So we can expand this determinant or find the value of the determinant in 6 different ways. If we consider first row, then we can find the determinants. Considering second row, we can also find the determinant. Third row, first column, second column, third column. So since it is of third order determinant, we can expand it in 6 different ways. If it is fourth order determinant, you can expand it in 8 different ways. So if it is nth order determinant, we can expand in 2n different ways. 2n. And all the values are equal. Now, say if I want to expand with respect to first row, then what we will have to do? We have to take product of elements of first row, any row we consider first row, elements of first row with corresponding cofactors. That is 311. It is A11 element, so it is 3 must be multiplied by cofactor of 3, that is C11. So minus 2 will be multiplied by C12. 6 will be multiplied by, since it is 1 3 element, multiplied by C13. So if we expand with first row, it will be 3 into C11 plus minus 2 into C12 plus 6 into C13. Now see, 3 into C11 is minus 1 to the power 1 plus 1 into M11 plus minus 2 into C12 is minus 1 to the power 1 plus 2 M12 plus 6 into minus 1 to the power 1 plus 3 M13. So since 1 plus 2 is 2, minus 1 to the power 2 is plus 1. So 3M11, it is minus, again it gives you a minus 1, so it is plus 2M12 it is positive, it becomes even, so it becomes positive, plus 6 m3. This is value of the determinant. Now m3 is, m11 is the determinant obtained by eliminating first row, first column. So it is 7, 5, 9 minus 3. Plus 2 into m12. I have to eliminate these two. So it gives you 8, 5, 2 minus 3. And it is 6 into m3, that is 8, 7, 2, 9. Again, following the same definition, we can expand this second order. And value of first order determinant is the value of the element. So we'll remember that for second order determinant, the value will be 7 into minus 3 minus 9 into 5. 8 into minus 3 minus 2 into 5. 8 into 9 minus 2 into 7. So that gives you value 3 into minus 21, and for 45 it is minus 45. Plus 2 into minus 24 and 10, so it is minus 10. Plus 6, 8 into 9, 72, minus 40, and dot, 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 dot. This is expansion with respect to first row. Second column. So second column is this. So first element is minus 2. So it is 1, 2 element. That is first row, second column. So minus 1 to the power 1 plus 2, m12. C12 is C12, this is. Plus, second element is C, 7. 7 is 2, 2 element. So it is minus 1 to the power 2 plus 2. Because it is second row, second column. Into m22. Plus 9 is there. It is third row, second column. Third row, second column. তাহলে minus 1 to the power 3 plus 2. M32. So after expanding, it is minus 2. It is minus, so it is, again it is minus 1. M12 plus 7. It is even into 1 into M22. It is odd. So plus 9 into minus 1. M32. So that gives you 2 into M12. M12, you have to eliminate first row and second column. That gives you these 4 elements. That is 8, 5, 2, minus 3. Plus 7 into M22, this element. So you have to eliminate this and this and this. That gives you these 4 elements. These 4 elements. That is 3, 6, 2, minus 3. Minus 9. It is minus 9. Minus into M32. You have to eliminate this row and this column. Only these 4 elements remains. 3, 6, 8, 5. So its value is 2 into, again minus 24 minus 10, plus 7 into minus 9 minus 12, minus 9 into 15 minus 48. You calculate this and you have this. Look at these two are equal. This way we find the value of a determinant. Expand it in this way. This is the expansion of a determinant. We can expand a determinant with respect to any row or any column. Any row or.
So students, that's all for the day. So what we learned today? We learned about few things about determinant. A lot of things left behind for the next classes. We learned about definition of determinant. What is determinant? What is rows of determinant? What are columns of the determinants? What is diagonal elements? What is diagonal? How many diagonals are there? Few types of determinants. Few types are defined. Diagonal determinant, scalar determinant, identity determinant, skew symmetric determinant, symmetric determinant, and few properties of skew symmetric determinants are discussed. Then transpose of a determinant, then minor, cofactor, and after that expansion of a determinant. That much we have learned today. I think you have understood what I want to teach you. So next, what is your duty at home? No need to consult any books. Just take a paper, construct few determinants, some of 2 order, some of 3 order, some of 4th order, not more than that. Now try to construct identity determinant of 2nd order, 3rd order, 4th order, diagonal determinant of 2nd order, 3rd order, 4th order, scalar determinant of 2nd order, 3rd order, 4th order, symmetric determinant, skew symmetric determinant of different orders. Now take transpose of all the determinants you constructed. Then find minor of the elements and then expand all of them. This is your homework. So that's all for the day. We'll meet in our next class. If everything runs fine, we'll meet at Friday 7:30. Up to that, goodbye. Stay home, stay safe, and be happy.